Distinguished ladies and gentlemen, Assalamu alaikum. My name is Kashan Jafri. I'm an associate member and the honorary secretary of the Royal Aeronautical Society's Pakistan division. Now, before we start today's lecture, I request all of you to keep your microphones muted until the Q&A session. During the Q&A, you can, of course, unmute yourself and ask questions from the speaker one by one. I welcome you all for the monthly lecture titled Global Warming Due to Non-Carbon Contrail Emissions of Jet Engines, which will be delivered by Dr. Sarah Qureshi, and her father, Mr. Masood Qureshi, will also join her during the Q&A session. Dr. Sarah Qureshi is the CEO and co-founder of Aero Engine Craft Private Limited, Pakistan's first commercial engine and aircraft research and design company that is developing environmentally safe contrail-free engines for the global aviation industry. Dr. Sarah has a PhD degree in aerospace engineering from Cranfield University, UK. Her area of specialization is aerospace propulsion, whereby she worked on development of a contrail-free aero engine that was derived from a patented technology. During her PhD research, Sarah assisted the inventor with patenting the contrail-free aero engines. Sarah has also recently co-invented and patented a supersonic commercial aircraft engine. She was awarded the Distinguished Aerospace Alumni Award by Cranfield University in 2020 for her leadership role and dynamic professional contributions to her field. In addition, she serves in the capacity of a visiting academic at the School of Aerospace at Cranfield University, where she provides technical feedback on research on environmentally safe aircraft engines. Sarah holds a private pilot license and also learned acrobatic flying while at Cranfield. Prior to this, Sarah completed her master's degree in the field of aerospace dynamics from Cranfield University, UK. Mr. Masood Latif Qureshi, her father, is the CTO and co-founder of Aero Engine Craft, is the inventor of the contrail-free aero engines. He has 3 patents granted for his inventions. He has an MSc in Physics and Electronics Engineering and over 45 years of scientific research experience. In this session, the speaker will talk about how the non-carbon emissions, that is the water vapors, are contributing towards increased global warming and how to tackle this situation by lowering the emissions. Now, without further ado, I request Dr. Sarah to deliver her lecture.
Ji, Assalamu alaikum. Thank you very much for the introduction, Kashan. I would now start with the presentation. We would be talking about contrails. Contrails is the most abundant non-carbon emission in the sky. On ground, when we talk about global warming and when we talk about fossil fuel burn or fuel burn, there are one major contributor to global warming, which is carbon dioxide, because the byproducts of any fuel consumption are carbon dioxide and water vapor. But on the ground, because you are at 1 atmosphere pressure, this water vapor recycles into liquid water and does not behave as a greenhouse gas. But when you are at a cruise altitude of 10,000 meters, the water vapor is just in the molecular form, and it is a greenhouse gas just as carbon dioxide is. So this issue is very critical because number one, it is happening in the sky. It is not very visible as other components of pollution are visible on the ground. Number two, the sole contributor to this pollution in the sky due to non-carbon emissions is the aviation industry, and this is a very specialized industry, and you require a lot of technical expertise. It's very tech intensive to deal with this problem. So in that case, when we talk about emissions, so we have to deal with 2 kinds of emissions. So contrail is basically the frozen component of water vapor that is released during hydrocarbon fuel burn in the air. And this is something that we have all witnessed when we fly, that the aircraft releases, these white thin clouds, which are contrails. So we have developed a technology to mitigate this, which is called the contrail-free aero engine. So the contrail-free aero engine is like an integrated turbo machinery which is attached to the engine at the end, and which processes the emissions of the engine and converts the water vapor component into liquid water, retains it on the aircraft, and releases a cleaner exhaust in the atmosphere. Okay, so now when we talk about the problem, contrail is basically, we just mentioned that it happens at cruise flight conditions at an altitude of around 10,000 meters, where the pressure is very low and the temperature is very low. And it is a byproduct, a combustion byproduct of hot engine exhaust emissions of water vapor. And they condense into contrails that later form artificial cirrus clouds. As you can see the contrails here, the freshly released contrails, and then these are the artificial persistent cirrus clouds that are formed. So at present, this is aviation's biggest environmental challenge because it affects the Earth's radiation budget, and the global warming potential of contrails is 5 times more than carbon dioxide. So carbon dioxide is contributing around 3 to 4% to aviation-induced global warming, whereas contrails are contributing 10 to 15% to aviation-induced global warming, and they are covering 0.2% of our atmosphere at present. This is an IPCC Intergovernment Panel for Climate Change report, which means that 0.2% of our atmosphere at the moment is covered not with natural clouds but with artificial clouds. Okay, so I'm just going to give you a reference because a lot of people come up with this question that the water vapor, when released from the aircraft, just recycles into liquid water as all other, water cycle that we know of on the ground and closer to the ground. But this is our reference altitudes. All our water weather cycle is below 2000 meters. You see, this is where you have these rain clouds. And when we are cruising at an altitude of around 11,000 meters, we are even above Mount Everest. So at this, the ambient conditions of around 218 Kelvin temperature and quarter of a bar atmosphere, there is no way that the water vapor can automatically recycle itself into liquid water. So it has to be addressed. This is a problem and it needs to be addressed. So one of our contributions is that we have developed a turbo machinery. It's an invention by Sir Masood Qureshi. That is an attachment to an existing aircraft engine that can process the combustion gases and sift out the water vapor content as liquid water and store it on the aircraft. And then when you are flying lower down in the atmosphere, closer to the ground, before landing, you can release it as water vapor or rainfall. So this work was given to me as a research question during my PhD, and since it had a lot of commercial promise and global impact, the university was very keen that this must be and should be taken forward. So after my PhD, I came back to Pakistan and I set up Pakistan's first commercial engine and aircraft R&D company with my co-founder Masood Latif Qureshi. And so with this company, we are trying to, we are working on sustainable aviation and on pro-environment aircraft engines and in addressing sustainable development goals, which are, there are global goals of climate change, water scarcity, innovation. And this is modeled as a circular economy in the sense that we hope that this can generate revenue for the aviation industry for its ease of adaptability through contrail emission trading and artificial rainfall. And this has been achieved through a breakthrough invention of a turbo machinery, which basically eliminates contrails at source, because I will discuss later the other methods of dealing with contrails. Are usually contrail suppression or mitigation after the contrails are released. But this is the only method where you prevent the formation of contrails. And we are using fuel emissions as a resource to recover water. Okay, these are the two technology patents that were granted within 15 months for this technology. And these are the milestones that we have achieved. This was, as I mentioned, that this was a problem stated during my PhD in 2012. And we moved through the invention and the scientific validation, through atmospheric physics, thermochemistry, mathematical modeling, and then the engineering model was developed. After that, the aircraft performance and engine performance analysis was simulated and carried out to analyze its impact. So, and the patents were filed. So in 2016, I submitted my PhD on this, and this was basically initially done on the A380 because A380 was the popular aircraft at that time, and it was the largest. The baseline specs were Trent 900 series because the A3 engine was the largest engine at that time, and if you can, verify or validate a model on a large scale, it is easier, to scale down. So that was also one of the objectives of using the A380 baseline specs. 2017, the patent was granted, and we launched our startup. We secured a modest amount of seed funding on equity sharing. And started the core product development. So we now at present we have alhamdulillah completed the core product development. It is under the testing phase, and inshallah sooner. Obviously there has been a delay because of the COVID, but inshallah we would be moving on to the next phase soon. And then we hope that we would be developing the same product on a large scale, on a commercial transport engine scale, and then testing and getting it certified. So our patents are valued at US dollar 2 million, and we can probably and very proudly call ourselves global first movers in contrail free aero engine design in the world. So this is basically just to explain where we stand in terms of technology. All technology that has to get airborne is rated on the basis of NASA's technology readiness level. This is a very popular standard. And basically it starts from 1, which is just a concept. And at 2, you develop a mathematical model. And at 3, you carry out simulations. Then you test it in the lab as component testing, component prototype testing in the lab, and then the system testing in the lab, and then testing in air and flying missions, and then you are ready for a commercial launch and 3RL9. So TRL1 to TRL3 is usually what PhD research is all about, and this is what I covered during my PhD. And when we launched our company, we started by TRL4. We decided to develop a proof of concept small scale model, 1 kilonewton baseline thrust jet engine, and integrated with the turbo machinery. That could later be, scaled up. So we started making components. Every component was individually tested for the jet engine, and the assembly of the jet engine was tested, and then the turbo machinery for the contrail-free device was developed, and we tested one version. Then there were some issues highlighted, and now we have developed a second version that is inshallah going to be tested soon. So we are basically at present at TRL6. So we hope to finish this phase by mid of this year, and inshallah then we would be moving to the next phase for developing the actual pre-production prototype of the technology. So I'm going to just give you some, business perspective first, and then we go on to a bit of a technical concept perspective. So this is any aerospace R&D industry is just like any other R&D industry. It is very technology intensive, and the way we budget ourselves is that almost 40% of our budget goes into equipment and machinery and materials. The remaining 40% goes into the human resource, because human resource is very specialized, and your overheads are the remaining 20%. Okay, so talking about the market, we all know that commercial aerospace is very monopolized and very controlled. There are only three engine manufacturers who are doing commercial transport engines, who are Rolls-Royce, GE Aviation, and Pratt and Whitney. Rolls-Royce has 25% of the market share. GE has 55% of the market share. There are around 55,000 commercial long-haul flight engines in service, and pre-COVID growth rate was 3.4%. So this is our primary market where we aim to sell this product. And our secondary market is the airframe manufacturers, because the Contrail aero engine would need to be integrated with the airframe for the storage of the water that is created. So the secondary market is again Boeing and Airbus, and again pre-COVID we had like 25,000 aircraft flying in the air, in terms of commercial transport. And then we have other stakeholders as well, which is the environmental agencies, which are Intergovernmental Panel on Climate Change, United Nations Framework Convention on Climate Change, AO, EASA, and then we have the COP26 coming up. But unfortunately, I mean, this is a responsibility that the entire aviation industry holds. As I said, that because this environmental contribution to global warming in the sky is not very visible, and it's so specialized that the rest of the world is not addressing it. And the aviation industry itself needs to address it, and also make sure that it is included in the agenda of the international climate change bodies for mitigating global warming and climate change. Okay, so this is basically, as I mentioned, that the concept is, you see, when you talk about environmental technologies, everybody is not interested unless you can create value out of it, because otherwise it just has to be limited to government grants, and that is not a sustainable model. So now they have new models which are called circular economy models. Circular economy models are pro-environment models, or social welfare models that create value, that generate value and make themselves sustainable. So our concept or our business model is also based on sustainable environment model. We have the Contrail free aero engine that is going to be provided to the engine manufacturer and then integrated with the aircraft manufacturer, and these would be then sold to the airlines. The airlines can either sell rainfall to local governments, or they can get Contrail trading credits for the global warming reduction, just like we had carbon credits. So we can have non-carbon credits as well. And so there would be a demand for environment friendly engines or aircraft by the airlines themselves. And then this is also like a technology backup for environmental agencies and regulatory bodies, because if you insist environmental agencies and legislative bodies to pass regulations on climate change to reduce contrails or CO2, they need an alternate solution. They need a backup. Because if they say that, okay, contrails, we should not have contrails, but there's no solution, nobody can stop flying. So when the technology provides an alternate solution, then that is when the regulatory bodies feel confident to pass their regulations. Okay, so this is just our, we are very actively seeking immediate investment of 1 million US dollar to promote this technology to the next level. We are finished with, almost done with our first phase of making the prototype technology demonstrator. And then in the second phase, we need to develop the industrial version, and which is another 2 years, and then another 2 years to product testing and certification. So now the business model is basically based on a patent licensing model, where we license out our technology to the OEMs, and they can then sell it, and they give us a licensing fee for every product that is sold. So basically, we have a price. The benchmark for patent licensing is 3% of revenue. So we sell a product to the engine manufacturers, and when they sell it ahead, whatever revenue that they generate, they have to give us 3% of that, and that would be the revenue earned by Aero Engine Craft. So this is how, so since we were expecting, this is extrapolated on the engine growth, annual engine growth of 3.4%. And this is, I think this is conservative, because post COVID, there would be a boom, and I think engine aircraft travel would suddenly expand, and there would be the growth rate might be higher. So this is just giving a profit and loss and development cost that we have. So initially, there's a development cost of developing the technology, and then later there would be just the administrative cost of selling the product, and this investment would be recovered in the initial years of the sale of the commercial launch of the product. So, so this is just, I'm going to touch briefly on the because a lot of people are from the aviation industry, and they have a lot of questions regarding the technological aspect. So basically, this is a method. This is a turbo machinery. It's like an addition to the family of gas turbine components. We call it the expeller, and basically the purpose is that the turbo machinery condenses the water vapor into liquid water within itself, and contains that liquid water, separates it out, and stores it on the aircraft during flight. Okay, so the research strategy was basically, we, we started. This is just how this work started. It's a very long journey, and we know that aviation timelines are generally very long. We have planes flying in the air that were designed 20 years ago. We have the Mirage in service at present in Pakistan, which is more than 50 years old. So this started with a basic study of contrails and water physics, atmospheric science, and condensation techniques. And once a technique was developed, it was it was simulated to determine the performance, how it would affect the performance of the aircraft engine. And then we looked at different things like a simple conventional heat exchange analysis, as well as using centrifugal compressors, the chemistry of basically emissions. And then all this, with all this, we came up with the design philosophy of this condensation system, and we developed the engineering model, and then this was simulated on an A380 aircraft on Trent 900 baseline specs, and the analysis was carried out. So I'm just trying, this is something I just want to explain. This is very important. It's something people don't understand, how contrails are formed. So basically, they are developed on the basis of the Kelvin equation, which is a function of the size, the ambient temperature, ambient pressure, and the saturated vapor pressure of water at that ambient temperature and pressure. And this determines the size of the water vapor or condensate that is formed. So at when if the size of the water molecule, no, I won't call it a molecule, but water particle formed is around 0.01 micron, this order, then it forms a cloud condensation nucleus. And so it is just a nucleus where all the other natural clouds would come and coalesce around it to form a bigger cloud. If it is in the order of 10 microns, it would form a water vapor or a cloud. and if it is 100 microns, it would form raindrops. So if you look at this, this is a graph, if it's visible, that this is our altitude from zero, above sea level, to 11,000 meters above sea level. And the particle radius that is formed is in the order of zero point 0.7 microns, right? So this is something like a cloud. It is still under 10 microns, so it is a cloud is formed. Water is not formed, right? And again, when we look at the actual conditions inside the engine, and our temperatures in the high power turbine, intermediate power turbine, low power turbine, three spool engine, nozzle, and the bypass. These are the temperature ranges, and at these temperature ranges and the pressure that is generated, our particle radius is negative. Negative particle radius, according to the Kelvin equation, means an unstable particle. That as soon as this water, molecule, water particle is formed, it just evaporates again into vapor. So it is not stable in the liquid form. And only at in the bypass, because bypass has no combustion, just the exhaust air is entering, we have the molecule size is 1 micron, which is again a cloud. So from here we understand that the atmosphere here is very hot. We don't even have clouds, we have steam here. Okay, so talking about contrail prevention, in the world there are two distinct methods. Either you disperse contrail into a vapor, that you make the size of the contrail, like contrail is in the order of 10 microns, so you make it smaller than 10 microns into 0.12 microns, so it does not remain a contrail. But the issue here is that even if it does not remain a contrail, it would still be a cloud condensation nucleus, and it would still be a greenhouse gas in molecular form. So as a greenhouse gas, even if water vapor does not manifest itself as a contrail or an artificial cloud, it still contributes to global warming. And then we have contrail nucleation into water, where you coalesce the smaller particles of water, and they form a larger particle, which is water, in the form of liquid water. So we started this by a performance analysis on a three-spool engine, both an intercooled recuperated turbofan engine as well as a regular standard turbofan engine. And just to know that maybe one of them would be more efficient. Okay, initially we also did like a simple heat exchange analysis, and the calculations showed that if you try to condense this water using a traditional heat exchange method like heat exchangers, you would need a heat exchanger which is the size of an engine itself, size and weight of an engine itself, to condense this water. So this is like essentially carrying another engine on the same aircraft. So then we have the other techniques. All these techniques are basically research-based techniques. Initially, the work on contrail-free aero engines started after World War II, and the purpose was because enemy planes could be detected by this white smoke coming out of the aircraft. So they determined, they started to look at ways in which the formation of the contrails could be avoided, either by changing the flight conditions or by using chemical additives. But then again, chemical additives don't solve our problem, because they just disperse the water vapor into smaller particles that are a greenhouse gas, and they in themselves are chemical pollutants in the atmosphere. So then I mentioned heat exchange method, which is which is not airworthy in terms of its size and weight. And then there have been other techniques, research techniques, that dispersion through, heating, microwave heating of contrails, or ultrasonic excitation. Like we have this, the very famous method of using silver iodide to, seed moisture and create rainfall. So something to seed vapors, clouds into ice. That was one research technique. And then trajectory optimization is like flying lower or flying higher in the atmosphere. And then what we are using is pressure-based condensation. Okay, so for pressure-based condensation, initially we also try to use the centrifugal compressor as a compression device, but there is, it is designed for the intake air at low temperatures. It is not a design for high temperature combustion gas. And then we developed this pressure-based condensation method to condense the water vapor, and this is basically the green exhaust concept. And first of all, it is a modular add-on attachment. We all know that now all turbine engines, gas turbine engines, in the aviation industry are modular because they are leased on performance by the hour, or they have different life. So instead of replacing the entire engine, one module like the compressor or the turbine is replaced. So similarly, our design is also modular, and it can be fitted on an existing aero engine behind the low power turbine and the in between the low power turbine and the core nozzle. Um, and then it can contain water vapor inside the engine. And then importantly, once you separate out the water, because it is 2% by mass flow, it is easier to further cool that water. Instead of using conventional engines where you have to cool down the entire gas, which is very challenging. And then this water can be used on board aircraft for maybe de-icing, or released at lower altitudes. So this is just the design philosophy of condensation, that you generate a pressure to which is at the exhaust temperature, which is equal to the saturated vapor pressure of water, so that the water vapor condenses. And then we also studied the thermochemistry of the gases, where there is an intergaseous exchange of energy, because water vapor has to lose its latent heat during condensation. So the other two gases among the combustion gases are carbon dioxide and nitrogen. And we found out that they act as a heat sink, and they absorb the latent heat of energy. And then there are several energy transitions within carbon dioxide and nitrogen as well, which also enable carbon dioxide to reduce its radiations, infrared radiations that contribute to global warming. So this is the theory is based on the vortex energy equation. And then we they were you know they, we went through a thermodynamic analysis, a structural analysis, stator and rotor blade design for the turbo machinery, the shell design and sealing, and the engineering model was developed. Okay, so this is just different stages of engine simulation. How there were some design point runs and off design runs. Basically, first we do off design, we determine the takeoff rating of the aircraft. That is our design point, because that is where you need maximum thrust out of the engine. And if you're so you have to design for that. All other segments of flight are off design conditions, like climbing or cruising or descent. So first we determined the design point, and then there were off design runs carried out, and at you determine the thrust requirement at cruise. And then there were different techniques where this engine was integrated. And then again the takeoff rating was determined. And because this device is not active at takeoff, so the takeoff rating does not change. And then whatever compensation or whatever trade-offs were um, determined during cruise flight. And again, the aircraft simulation was basically also carried out just to determine that there is a maybe 20% or 30% increase in the engine weight and the engine length, and how that would affect the aircraft. But the overall weight, it is a very minimal portion of the overall weight of the aircraft. And because it is aligned with the core geometry of the engine, the aerodynamic performance of the aircraft is not affected. So the emission index of water for hydrocarbon fuel burn or kerosene fuel burn that we use, jet fuel, is 1.25. So for 1 kilogram of fuel, we release 1.25 kilogram of water vapor. And in the Airbus, this was around 1.34 kilogram per second of water produced, because Airbus burns around 1 kilogram per second of fuel. I mean A380, not Airbus, per second. So this was like 160 tons of water produced during an 8-hour flight. So basically, our outcome is that we prevent contrail formation and reduce the global warming that is created through the contrail, and in the process obtain water. Okay. So this was basically carried out with the a multidisciplinary approach. We had to study atmospherics, physics, thermochemistry, engineering, thermodynamics, aircraft performance, engine performance, and this is like, basically this device is like an art to part. It was just a concept on a paper, which was then you know developed and patented. The idea and the mechanical functioning was patented, and then the entire analysis was carried out and the mechanical model was made, and now we have developed the actual engine prototype. So still, there's always room for research. Um, I have a visiting academic position at Cranfield University. Some of the students keep, for their master's thesis, they pick one topic and they carry out some research on different aspects to improve them further. And then we have this, some suggestions for prototyping, and this is our team basically. And the company was incubated at NIC Lums. Karandas provided us equity uh, basis, some seed and investment, although that is not exactly what somebody would look at an investment in the aviation industry, because they had this women program which was providing some support to women who are making clothes and handbags and all. So, but it just helped us launch our company and, at least develop the prototype. And so we have been trying to get some collaboration with the Pakistan Aeronautical Complex, as they have a lot of facilities available, and they are close to our working site as well. And at Cranfield, I have a work visiting academic position. So this is just the academic side of R&D keeps moving ahead through that platform. This is our contact and some links available on social media, and some public knowledge about our work. That's my daughter, and this is an RB211 engine at our university museum. So, okay. So this is basically the end of the presentation. Now I would like to, can you hear me well?
Yes, we can hear you.
Okay, because the internet connection is not very strong, so I just, if you can't hear me, just type a message. Okay, so I'm going to run this product. This is something about our company, our work. Is the painting, is the video clear?
Yes, ma'am, the video is clear.
हमारा जो रिसर्च प्रोजेक्ट है ये ग्लोबल वार्मिंग को कम करने का, उसमें से एक हिस्सा जो कि पानी जो एग्जॉस्ट निकल रहा है इंजन में से उसको कम करना है, ख़त्म करना है। मुख्तलिफ तरीके हैं दुनिया में जो जिन पे आजकल रिसर्च हो रही है। कोई उसको डिसिपेट करना चाहते हैं, कोई उसमें क्रिस्टल्स डाल के, कोई उसमें केमिकल्स डालने की कोशिश कर रहे हैं। ये सारी चीज़ें जो है ना, एक फ़ायदा होता है तो एक नुकसान होता है। तो हमारा मेथड जो है, जो हमारी इजाद है, वो इसी पानी को कैप्चर करने की है, जो technology in itself is very challenging. When you talk about radical technologies or disruptive technologies, they're not very well received. It's very difficult to convince people to look at it from a different perspective. I see a lot of activists who are just focused on the climate change on the ground, and I think we all need to look up into the sky. It has its repercussions on the earth, and it is the earth's atmosphere that is at risk. They're both greenhouse gases. They're both
due to global warming. और ये जो वाटर वेपर्स हैं, जब ये आप आसमान में निकलते हैं, क्योंकि वहाँ पे दर्जा हरारत बहुत कम है, तो ये एक मसनूई बादल बना देते। If, for example, they say no contrails from tomorrow, I mean that's not a solution. Nobody can stop flying. Planes have to fly. So there has to be an alternate, or there has to be a backup technology that says that yes, we have a solution to this problem, and if there's a regulation that makes if the aviation industry comply to these standards, we would be supporting that. I'm Dr. Sara Qureshi, CEO and founder of Aero Engine Craft Private Limited. We are developing the next generation of environmentally safe aircraft engines for the world. And my observation and my suggestion to you will be in the context of climate change as well as regulations. I believe that at present on the global front, all regulations and efforts towards climate change are focused on the ground, and unfortunately we are neglecting the Earth's atmosphere, which is even a bigger threat to climate change than the ground, because there are no offsets in the atmosphere. You cannot grow trees, and there's a limitation to the kind of technologies that could be transposed in the air. So the climate change to aviation in the atmosphere is a looming threat. And so far, since I guess the aviation industry is so monopolized and so controlled, we really don't have any regulation or by any of the international bodies on climate change, including the UN. So I would request you to look deeper into this matter, and it has to be done on an urgent basis. Thank you.
Thank you very much. Okay, so over to you, sir.
Well, I want to thank this last intervention, because it was the only one that really gave a suggestion, and a very valid one.
Okay. And then this was a long video, but if I can find, I just want to show you a project concept animation. This is just 30 seconds. There's no music with this. ओके अच्छा, और एक हमारा जो हमारा फर्स्ट जेट इंजन फायरिंग हुई थी, you can see the engine revving up. Okay. So This is it. You can see that, we are trying to work on both fronts. We are working on the technology development, and that too, we are trying to develop capabilities from a scratch and building it up. It's not like a turnkey solution being imported from China. The engine that we developed is almost 95% in-house components. Even 90% of the engine is manufactured within our own facilities. And secondly, we are also trying to promote this concept of sustainable aviation technologies in the on the global front, with regulatory bodies, and trying to create awareness around that. और अब I think we are both open to questions. My co-founder, Sir Masood Latif Qureshi, is also here. I'm also here. We can, we can answer your questions if there are any. And thank you very much for your patience and for listening. It was quite a long presentation.
Thank you. Thank you very much for the wonderful presentation, ma'am. We have a question from Dr. Ahmed Azaz. I'll unmute him and we'll ask his question.
Assalamu alaikum, Dr. Sarah.
Ji, walaikum salam.
Thank you very much. I must appreciate the level of technology development that you have attained and achieved. I must appreciate that both you and Sir Masood Latif are excellent performance and progressing. मुझे सिर्फ ये पूछना कि do you plan to develop commercial engines as well, or just use it as a facility for your patent to be proven and developed? So are you working on both the sides, or just the one you made patent for?
Okay, sir, are you the one from Camera?
Of course, I was there, but now I am retired.
जी जी, तो आपको आपसे तो मुझे तस्वीर नहीं आ रही आपकी, तो आपसे तो हमारी मुलाकात है ना?
Of course, मैम, वही बिल्कुल कैमरा वाले।
जी जी, तो मैं सबसे पहले तो आपका बहुत शुक्रिया अदा करना चाहती हूँ ऑन दिस फोरम। आई थिंक सबसे ज़्यादा जो हमें टेक्नोलॉजी में टेक्नोलॉजिकल हेल्प मिली है और सपोर्ट और असिस्टेंस मिली है इन रियल फॉर्म, इट वाज फ्रॉम यू। और जिस तरह जो हमें जो एक स्टार्ट मिल गया, जिस तरह आपने हमें उस वक्त हेल्प आउट किया, तो वी आर वेरी ग्रेटफुल, very grateful to you, and inshallah we have planned, Qureshi साहब ने कहा था कि जब भी we will plan a engine firing ceremony, you would be our guest of honor. So
I'm so honored. Thank you very much.
I'm so glad that you joined us. I would like Qureshi साहब to answer your question.
Yes. Okay. Well, it's a journey that started with our requirement for a jet engine in order to test the device to control condensation. Now, so we found a certain number of difficulties in acquiring an engine, and something very expensive beyond our budget and all other things. So we started on the beg, borrow, or steal. So usme then finally we gave up and we said, "Chado pare, we'll make our own engine." So we started out on the engine now, and the device went on a secondary level, and the primary effort was for developing this engine, and for which you were very helpful. You were very helpful, and it sort of kind of put us on the track on making these engines. So, and then of course, once there will be a time when we'll have many different models of these engines coming up for different applications. So for the time being, we are more focused on the thing, and this is just a 1 kilonewton engine that we have designed and built, and it's in the last stages of perfection. There are some bugs that we discovered in it. So once that's over, then our device would be tested. Our device is ready, right? It requires a engine to start with. Okay. Short of that engine, there was always the suggestion that by Dr. Dr. Izzaz of IST, Institute of Science and Technology. And he said that why don't you just go ahead and make a burner that would give you the exhaust uh, at that temperature and pressure and airflow. And then, of course, we did work a bit, but then we found that that was more difficult to get this level of exhaust and thrust. So we reverted to the jet engine as such. So, and I hope that we need your prayers and your
Definitely,
further
sir.
in going further and making different models of the engine as well for a commercial reason. And this thing is, of course, for a global warming reason. So we
Mashallah,
have
mashallah.
I think,
Excellent, sir. Keep it up. All my prayers with you, sir, always.
Thank you.
Thank you. Very much. Okay. Are there any other questions by any other from the
Yes,
audience?
I do have a question. My question is regarding fuel efficiency of the device, because as Dr. Sara said during the lecture that for 1 kg of fuel consumed, the engine produces 1.25 kg of water vapors.
That's right. Yes.
And that those water vapors will be stored on board the aircraft.
Yes.
So commercially, wouldn't that be a trade-off? Because when fuel is consumed, the aircraft weight lowers, and the engines have to use less power to keep the aircraft in the air. But if you are
That's
going
right.
to produce more water than the fuel on board, if you are going to produce more weight on board, then what are the commercial trade-offs?
Yeah, that's right. Okay. Now, it's really a chemical equation. That's just the number of atoms of oxygen versus all the carbohydrates, the carbon, and the hydrogen, and then, of course, when you create water and carbon dioxide, the end result of water is, because we have taken in a lot of oxygen. I mean, we've taken the oxygen from the air, so that is what's contributing to the increase in weight. Okay, that's all right. I mean, that's on the side, but now the the aircraft would be definitely getting heavier. You're right. You see, because and normally the planes are designed to land at a much lower weight than their takeoff weight. This is because of the strength of the undercarriage and all those other issues that take place. So we shall be dumping this water. Now, if we just release it, it will come out and again create a cloud. So it will be a zero-sum game. Now, what we contain it, and we have to cool it. It's at a very, very high temperature. I mean, it's about 350 degrees centigrade. That's quite a temperature. It's in a pressure vessel and in pressure pipes, and it's then, of course, piped through the aircraft's, let's say, leading edge, so that it should dissipate heat and use some heat here and there, and then only can we throw it out, because otherwise it'll be a burst if it is released. Then it has to be brought down to a certain condition, and it can be then released in batches. And it's a huge, only the surf, I mean, a huge drop, let's say a huge drop of water, where the surface, of course, would evaporate, but then the core, water in the core, by the time it comes down at a more comfortable temperature, atmospheric temperature, it should remain as water. Now, this can't be dumped on cities and things, but then there are places like overflying farms, and you have overflying the desert, and you just drop this. Then at the tail end, of course, there is the commercial aspect that suppose if you're landing at in a desert city, uh, and they want to grow a forest, they can have like Dubai can have the option of growing a forest outside. So every plane that comes in dumps its share of water and comes down, and they also get paid for the water, and the forest also get, develops. I mean, these are just things that I'm talking out of fantasy. But the main thing, your question is, of course, answered that it would be dropped in, and there'll be batches, and as a batch form, it will be.
Sir Masood, I have a suggestion. In commercial flights, there is always a requirement for the flight to carry water for the passenger usage.
Yes.
So, if they can reduce that water need in the takeoff phase and then later on refill it with the onboard generation of water through your regenerative or recuperative system, then I can see the more fuel carriage capacity will be increased, and definitely it will help the airlines to carry less water in the initial stages.
Yeah, well, this water, of course, theoretically it's only H2O, but it's going to contain. We expect that it will contain certain soot from the engine, and it will maybe if there is some sulfur, there is some sulfur dioxide. There can be nitrates. It can be it's like a fertilizer if it contains nitrates. And this water is can absorb anything from the exhaust. Okay, and therefore, of course, not as drinking water, but it can be used to things like flush toilets and things like that. But first, it has to be cooled and brought down to a certain room temperature. And what we are now going to face in the next phase is how to cool this temperature down, and so that it can be discharged and can also be used. Then, of course, in the leading edge, cooling, de-icing, and other things like Dr. Sara just mentioned, of course, these are the first obvious uh, places to dissipate heat. And there could be more ideas and more places later on.
See, I just want to add to this कि there's also another dimension. जो हम we are as aviation engineers, we are trained to think like this. We always think of the fuel, and because fuel is expensive, it would need to burn more fuel. But then when we are designing for the environment, then our design parameter is very different. Our design parameter is a quantitative parameter of global warming potential. It is actually something that they measure. See, so when you look at yes, there is because this is engineering. This is not magic. There are engineering design is always a compromise and trade off. So yes, there is going to be some extra fuel penalty and cost related cost, but then when we look at the global warming potential, as per our initial calculations, it is reduced by 60%. So then it depends that where आपकी priorities कहाँ पे हैं. Like it is just like saying that okay, making masks and ventilators is very expensive, but the priority is saving lives. It's not the cost of the medicine or the ventilator. Similarly, if the priority is to we have to deal with this issue of global warming and climate change in the atmosphere, then this is something that we have to do this. And you can see this model in the automotive industry. The your engine has exhaust gas recirculators, catalytic converters, this, that, and the other. And the OEMs as well as the consumer are paying for it because you have to reduce the emissions on the roads. And it is also, these components are also reducing the performance of the car, but we are going with it. So we have to adopt this approach in the aviation industry as well. लेकिन जैसे मैंने आपसे पहले बात की थी ना कि एक some things are widespread knowledge, like CO2 emission on the ground is a very widespread knowledge. Automotive industry is a very widespread knowledge. So people are dealing with it, and there is a pressure on the industry itself as well. But aviation is a very niche knowledge. People don't know about it, and even within the industry, people are very divided. When you talk about contrails, I've spent 5 years during my PhD. There are thousands and thousands of research papers on every aspect of contrails and peer-reviewed journal papers, and they all, there is a scientific consensus of the scientist community that contrails contribute a minimum of 5% more to global warming. But within the industry, people are still dismissing it. अभी एयरबस ने पूरा हाइड्रोजन की अपनी फ्लीट लॉन्च कर दी है. They want to have by 2035 the industry wants to be on hydrogen by for short haul, and 2050 long haul के लिए अभी they are using liquid hydrogen. There is no other choice. ठीक है, लिक्विड हाइड्रोजन में आप 3 गुना ज्यादा कॉन्ट्रेल बनाएंगे. यू विल नॉट सी अ ब्लू स्काई, यू विल सी अ वाइट स्काई, बट नोबडी इज टॉकिंग अबाउट इट, जहां तक मुझे पता है. ठीक है, सो these are the choices that we have to make.
Thank you for the
Right?
detailed answer, ma'am. Okay, if any of you have any question, please unmute yourself and ask question. Yes, Saad, please introduce yourself and ask your question.
Okay, my name is Saad, and I have a background in mechanical engineering. So my question, first of all, thank you, Dr. Sarah and Mr. Masood, for this presentation, and it gives a lot of sense of pride that someone from Pakistan are working in the R&D sector of this aircraft engine design. So my question is that since you have mentioned that your device is somewhat at the TRL6 level, and soon you will be moving to the TRL7 level. So for that requirement, you need to have a platform engine which will serve as a demonstrator engine for your device. So what are your plans for this particular engine? Because this, I think, from my side, I think that this engine is going to be from the commercial wide engine body aircraft engines. So what are your plans for that demonstrator engine?
Okay, yes, you are right. This is how we are planning to move. Number one, now we are, we are seeking funding for the next phase, because and we need, because now initially the design was done on the A380, but now at present the most popular aircraft is the A320 and the Neo engine, or the CFM 56 derivatives. So we are in the process to get hold of one engine, and that can be used as the test engine for testing the full scale device. And it doesn't need to be an airworthy engine, it can be a grounded engine, and they're not very a lot of options, but we know some people who can who are trying to who import such engines, or get them auctioned, buy them in auction from PIA. So this is the plan for the future. Sir Masood, would you like to add anything to this?
Well, you have answered it perfectly, and I think that this is something that we should be doing in TRL 8 level, and once we have accomplished TRL 7 with the engine that we have. So I think that that was a good explanation you gave. And it was a very good question. Okay, so is there any other questions?
इतने कम क्वेश्चन हो इसका मतलब होता है किसी को कुछ समझ नहीं आई
हैं? नहीं वो सब नहीं I'm sure it was very thoroughly explained.
That's also one aspect. It was very well explained. The lecture was very well explained. I have one more question. Whether this water that is stored on board could be used for re-injection and subsequent thrust augmentation for the engines.
Yes,
Is that possible?
It can be used. And then there is, of course, there's some portion in which you have to heat the air that is coming in. And of course, there is and then, of course, the intercooler, and then,
because that could be an efficient use.
Yes, but this is it's a very small use of the total quantity of.
Total quantity, we are talking about tons of water on board.
The amount of heat that contains. I mean, you
yes.
Visualize the amount of heat of the amount of energy required to go from, for the flight, for a certain flight, and the amount of heat generated is colossal. And then, of course, that is now being taken up, partially is taken up by the water vapor. Yeah, the water vapor itself is emitting heat, which is, of course, going out through the exhaust. But this is just the latent heat of condensation, which is being absorbed, and we have worked it out in a way that a portion of this heat would be absorbed by nitrogen. Okay. So it will be a hotter nitrogen coming out of the exhaust.
Of the exhaust, yes.
One of the side things that's happening. But this water, the quantity is too much, and the heat content is too much. Of course, after using it here and there.
मैं सिर्फ इसमें ये ऐड करूंगी कि ये जो वाटर इंजेक्शन होती है ये कंबस्टर में की जाती है and the purpose is to reduce NOx content because NOx is a function of NOx generation is a function of very high temperature. तो इससे सिर्फ they try to lower the temperature in the combustor ताकि NOx जो कि parts per million में produce होती है उसकी क्वांटिटी कम हो बट अगेन सर ने जैसे कहा है कि इट्स अ लॉट ऑफ वाटर तो वो मतलब आप कुछ आप उसका यूज उस पे निकाल लेंगे लेकिन आई थिंक देयर कैन बी मच मोर एफिशिएंट यूज ऑन द ग्राउंड इफ वी आर सक्सेसफुल टू रिलीज इट like sir mentioned that you grow a forest around Dubai or in Africa or grow crops so if it is efficiently used it has a much greater potential.
Yes, it has. Thank you. We have a question from Fayed Ishtiyaq.
Assalamualaikum. My question is that most of the airlines look at the lifespan of the particular devices. So I want to ask how much what is the projected lifespan we can expect from this device?
इसका वो तो आपको ना एक you have to go through very rigorous fatigue analysis and life cycle assessments device ke. But as I mentioned that this is a turbo machinery, right? So the way you have so this is something which would be closer to a turbine because it is processing hot gas. It's processing hot emissions and you would need the same materials and there is maybe the rotation speed is different. So जो उसके साथ ही ये जो technology it's very synergistic. So it would be very close to जो कि आपकी turbine का low power turbine का life cycle होता है.
Thank you, ma'am. And I guess we'll now move towards the end of the lecture. I'll now invite Air Commodore Rashid Hussain Siraj, Vice President of the Royal Aeronautical Society Pakistan, for his closing remarks in the lecture.
Assalamu alaikum, ladies and gentlemen. Can you hear me?
Walaikum salam, sir. Yes, we can hear you loud and clear.
Walaikum salam.
Okay, we heard a very interesting lecture. And I think this is the second in the series. We had heard an earlier lecture by Dr. Sara on the subject. And although this is the second time I'm listening to a similar lecture, but this was also very different in many ways. And I've come to know a lot of new things that I somehow missed out in the earlier lecture. There is no doubt that Dr. Sara and Dr. Qureshi have done an excellent work, and particularly with the very limited financial and technical resources at their disposal. Now, it is also more commendable the fact that Dr. Sara happens to be a female, and all R&D in the field of aviation is more a male-dominated endeavor than a female, and that also from a third world country like Pakistan. So it is very commendable of the kind of work that they have done and the direction they are taking and the future that they envisage in terms of the work that and the research that they have done. Now, there were some very interesting questions, although not many as we had expected, but the few questions that were asked, some of them related to the cost-benefit ratio. And we will have to see whether how much is it going to cost to develop the whole system and to install it on aeroplanes and to make it operational, and whether that kind of cost is going to be acceptable, not only the cost of the device itself, but also the cost of carrying all the water on board, building new tanks for them in which the water can be stored, and dumping it at suitable sites and the cost that is involved in that. So there's going to be this cost, but like Dr. Sara said very correctly, that what is more important is global warming, climate change, and climate change is in focus these days, particularly with America coming back on board. That is global warming and the effects that is bringing in terms of droughts and floods and food security and a loss of other miseries to the people. Is controlling that more important, or is it more important to save money in terms of operating of the aeroplanes? So while there is no doubt that's very important that pollution should be controlled, that greenhouse gases should be controlled, that global warming has to be, if not reversed, at least it has to be reduced as far as is possible. And this device might contribute significantly to that endeavor. So from that point of view, it's a very important innovation. The challenge I see, the greatest challenge would be to be able to convince governments to mandate the reduction of contrails, whether they do it by means of this device, or whether they mandate the airlines to fly either higher or lower than the altitude at which contrails are formed, which would mean some kind of air traffic management as well as higher operating costs. But these are some of the challenges, and I'm sure as the importance of controlling climate change and global warming becomes more apparent and becomes more forceful, governments will have to take certain measures to ensure that contrails are minimized or eliminated altogether. So my congratulations once again and my appreciation to the team for doing an excellent work. I must thank on behalf of all of us for an excellent lecture that was developed by Dr. Sara, and we look forward to not only to her success, but also to getting benefited from her research in the future. Thank you very much, Dr. Sara and Dr. Qureshi.
Boss Shukriya, thank you for your encouragement, sir. And I would just like to add that, जैसे आपने कहा कि the implementation would be a challenge, but when I look at if you look at the hydrogen program that the Europe is very actively pursuing, मतलब वो अभी मेरी समझ से तो बाहर है कि वो it is so radically disruptive that they have to change the airports, they have to change the aircraft, they have to change the engine, but they are still going for it. So when I look at that, I think that what we are developing is not that disruptive, and inshallah it would not be that much of a problem or a challenge to implement it. लेकिन आपकी हौसला अफजाई का बहुत शुक्रिया, and I think this is a very good forum. come across some very enlightening and knowledgeable lectures on this forum. So I would like to, thank you and your team for this effort, which is creating so much awareness on different aspects of aviation. Thank you very much.
Thank you very much, Dr. Sara and Dr. Masood Qureshi. With this, I thank all the participants for joining our lectures regularly. If you have any questions regarding membership, please feel free to contact me. Thank you once again. Allah Hafiz.